Now, what is a systems? How do we define a system of linear equation? A system of m linear equation in n variable is a set of m number of equations, each of which is linear in the same n number of variables. So notice that, okay, here we will have m number of equation in n unknowns. And for example, in equation 1, we have a sub 11 x sub 1 plus a sub 12 x sub 2 plus a sub 13 x sub 3 plus dot 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 plus a sub 1 and x sub n equals b1. Equation 2, we have a sub 21 x sub 1 plus a sub 22 x sub 2 plus a sub 23 x sub 3 plus dot 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 plus a sub 2 and x sub n equals b sub 2. And notice that as we go down, the subscript, the first digit of the subscript of the leading coefficient is simply the number of the equation. And the last digit of the subscript of the last variable is the last number of variable. Now, a system of linear equation is also called a linear system. A solution of a linear system is a sequence of numbers s sub 1, s sub 2, s sub 3, up to s sub n, that is a solution of each equation in the system. Okay, we're given here 3 examples, 3 pairs of equations in 2 variables. Now, how do we solve it and graph each system of linear equations? So we're asked to solve as well as to graph each system of linear equation. So for the first pair, we will have x plus y equals 3 and x minus y equals negative 1. It's obvious that if we add the 2 equations, okay, we'll be able to eliminate y and we can solve for x. So that x is equivalent to 1. And applying our back substitution here, so if we substitute x to be 1, we can solve for y. That will be 3 minus 1. Then y is equivalent to 2. Notice that the point 1, 2 is the solution, okay, for the 2 equation. 1 plus 2 is 3. 1 minus 2 is negative 1. Now, how do we graph it? Now, we can actually apply, the easiest technique is to apply the intercept form. So let's say for the first equation, if allow x to be 0, y is equivalent to 3. And if y is 0, x is equivalent to 3. Say here, just roughly. Okay, then we simply connect the 2 points. I'm sorry for that. So just imagine it's a straight line. And then we will have the second equation, x minus y is negative 1. So if x is 0, y is equivalent to 1. And then when y is 0, x is equivalent to negative 1. And then we simply connect the points. Okay, so notice that the 2 lines intersect, okay? And actually, so we can see here that the 2 lines intersect. And this point of intersection is actually the point 1, 2. Okay? This is the point of intersection of the 2 lines. So this means that these 2 equations are actually intersecting lines. Or that whenever a system has one unique solution, that point, that solution is actually a point of intersection. Okay, what about for letter B? We will have x plus y equals 3, and you have 2x plus 2y equals 6. And we can see that equation 2 is just a multiple of equation 1, right? So if I multiply equation, say equation 1 by negative 2, okay, we have negative 2x plus 2x is 0, and negative 2y plus 2y is also 0. Negative 6 plus 6 is also 0. So this system tells us that there are infinitely many solutions There are infinitely many solutions, okay? Now, how do we find the solution set? We can actually represent the solution in terms of a parameter, right? So since we have infinitely many solutions, we can solve for x in terms of y. So that is x is equivalent to 3 minus y. And we're going to let y be a parameter t. Say, let y be equal to t such that t is any real number. So that x is simply 3 minus t. Now we can have it in coordinate form. Let's say the solution set is given as 3 minus t and then t. Okay, so that one particular solution, let's look for one particular solution. Let's say let t be equal to 1. Okay, if t is equivalent to 1, then x is 2 and y is 1. Now we can test this point to satisfy the two equation, and it will satisfy. See here, 2 plus 1 is 3, 2 times 2 is 4, plus 2 times 1 is 2. So 4 plus 2 is equal to 6. And consequently, the graph is simply coincidental lines. Okay? So if x is 0, y is equivalent to 3. And if y is 0, x is equivalent to 3. So we will have actually coincidental lines. So again, if we're going to let x be 0, y is still 3. And if we're going to let y be 0, x is equivalent to 3. So we will have a set of coincidental lines, and all the points in the line are actually solution to the system of equation. Now, in example C, we will have x plus y equals 3, x plus y equals 1, and say if subtract the two equations, say equation 1 minus equation 2. Okay, equation 1 minus equation 2. What will happen? Have x minus x is 0. Y minus y is 0. 3 minus 1 is 2. But 0 is not equal to 2. It's a false statement, and hence the system has no solution. Okay, so the system has no solution, and we can see that the graph of these equations is given as parallel lines. Okay, so again, if x is 0, y is 3. If y is 0, x is equivalent to 3. So roughly, say we will have that one. Say that's 3. And x plus y equals 1. So when x is 0, y is 1. When y is 0, x is equivalent to 1. So actually, we will have, sorry for that. Okay, this line should have the same slope. Okay, just imagine that they have the same slope and with different y and x intercept. Okay, that's why there is no solution. There is no point of intersection. So with these three types of system, we can come to a conclusion that the system can have one unique solution. The system can have infinitely many solutions, or a system of equation can have no solution at all. Okay, so with that, we can classify a system of equation based on the number of solution. So we will refer to a system to be consistent for a system that has exactly one solution. Sometimes they refer to that one as consistent independent. Okay, sometimes they refer to this one as consistent independent. And for the system that has infinitely many solutions, we will refer to it as consistent dependent. Okay? And for a system that has no solution, we will refer to it as inconsistent system. Now, we can also solve the system of linear equation using the method of, we can solve it and rewrite the system in what you call row echelon form. Now, what does a row echelon form looks like? First is we add. No? If we are going to add equation 1 with equation 2, and the result will be the new equation 2, obviously we will have an equation 2 that is in terms of y and z. And then if we multiply equation 1 by negative 2 and add it with equation 3, we will able to eliminate this and come up with equation 3 in terms of y and z. Okay, so let's see it here. So here we were able to add equation 1 and equation 2, and we will arrive at the new second equation. And then multiplying equation 1 by negative 2x, multiplying equation 1 by negative 2 and add it to equation 3, this which produces a new third equation. We will have now equation 3 and equation 2 in y and z. And the next technique is to remove y here by adding equation 2 and equation 3, so that the last equation will be in terms of z. And now we can solve for z, which is just equivalent to 2. And by applying back substitution, we can solve for y. Say y is equivalent to 5 minus 3z. So that would be 5 minus 3z, and z is equivalent to 2. So that y is equivalent to negative 1. And here, by applying back substitution, we can solve for x. You will have 9 plus 2y, but y is negative 1, minus 3z, but z is equal to 2. So you have 9 minus 2 is 7, minus 6 is 1. So hence, x is equivalent to 1. We can write the solution in terms of coordinate form. We'll have x is equivalent to 1, y is equivalent to negative 1, and z is equivalent to 2. Notice that if I'm going to use this point and satisfy the system of equation, substitute x and y in the three equations for the system, we will see that it will satisfy the equation. Okay, now since we were able to come up with a solution, that means all these three equations here. Okay, by the way, we will have three, since we have an equation in three unknowns, the graph is a plane. So this simply tells us that these three planes intersect at the point 1, negative 1, and 2. Okay, so they all intersect at the point 1, negative 1, and a system of linear equation is simply a set of linear equations. It can be in m number of equations, in n number of unknowns. Now, a system of equation can be classified as consistent independent, consistent dependent, and inconsistent. So for the first type, we will have one unique solution. For the consistent dependent, we have infinitely many solutions. And for no solution at all, okay, then that will be for an inconsistent system of linear equation. What else? So aside from knowing the classification of system of equation, we were also we were able to know how we can solve a system of equation, basically by elimination using addition. And also we can rewrite the solution in terms of we can solve or we can show the elimination using the row echelon form. Okay, so that will be all for the first lesson. The upcoming lesson will be all about an algorithm called Gaussian elimination and Gauss-Jordan elimination. See you